Hi everyone. So in this video we will take a look at how the earth can act as a spring. So what we have done is we have sort of taken the earth. This is my earth over here, this circle, and we have dug out a hole through the center of the earth. Well, that's kind of unreasonable, but let's say that for the purposes of our problem we can do that. And then if you drop a mass, let's say a tiny ball with mass m, if you drop it in that hole from one side, you can sort of see that it's going to start going downward because the earth is going to start pulling it. But I think this is going to work out to be just like a spring SHM, where the mass goes all the way to the other side and keeps going back and forth between the two ends of that hole. All right, so we will try to see how that works out. So in order to see that, we have to know something. So for instance, we have to figure out how the Earth's gravitational field, or the force of gravity on this mass m, changes as this ball goes closer and closer to the center of the Earth, right? So here I have this variable r as a function of time. So you can think of the ball moving downward and its radius, or the distance from the center of the Earth, changing as a function of time. And so we're going to use that variable, but we'll also have to know what the force on this mass m is. And this picture, the bottom picture over here, shows the function, the gravitational force as a function of distance from the center of the Earth. Now this is something that we did in chapter 11 when we were talking about gravitation in University Physics 1. But if you have missed it, I have put on some of the slides in the appropriate folder for you to take a look at and figure out what's going on. But we can go over this very quickly. So what happens is, if we consider the mass situated over here, then the force that is acting on this mass is only the gravitational force due to the stuff that is inside this circle in this region, right? So we got to figure out how much mass of the Earth is inside this circle, and then using that we can figure out the gravitational force. So generally Newton's law of gravitation tells us that the force of gravitation is at a distance r, and put a vector sign on it because this is a force, so it's a vector. And the vector is radially inward, so it's going to have a negative sign, and I'm going to use the r hat vector. R hat represents the unit vector along the radial direction. In this case, notice that the ball is always moving along the radial direction, so we can use the r hat vector to denote this force. Okay, and then Newton's second law Newton's law of gravitation tells us that this force is equal to g times mass of whatever is pulling the ball times the mass of the ball divided by its distance from the center of the gravitating object squared. Okay, now what is the mass that goes in here? That's the mass of the Earth that is inside the sphere, inside this smaller sphere of radius r. So we're going to assume that the Earth is uniformly distributed. Its mass is uniformly distributed. That would mean that the mass that appears over here is just the total mass of the Earth divided by the total volume of the Earth, which is 4/3 pi radius of the Earth cubed, multiplied by the volume of the sphere that is inside over here. So that's 4/3 pi r cubed. Now if you do the algebra, the 4/3 will cancel, the pi will cancel. So this part turns out to be me r cubed over r cubed, re cubed, where re is the radius of the Earth. So let's plug this back into our expression for Fg, and then we get Fg, which is a function of r, equals negative g times little m multiplied by me r cubed over re cubed, and then in the denominator we have an r squared times r hat. So this r squared from the denominator will cancel with the r cube in the numerator, and we will eventually get negative g little m capital M e over re cubed with an r times r hat. So now let's compare this force with our force for the spring. So for the spring plus mass, That SHM, the force F looked like negative kx times x hat, right? Where k was a constant, k was the spring constant. Compare this with our force of gravity over here. So that force looks like Fg is equal to negative some constant times r hat. And this constant here is gm me over re cubed, right? So this is kind of comparable to our spring constant in the spring mass system. We can simplify this a little bit further. Remember, in gravitation we learned that g times mass of the earth is equal to little g, the acceleration due to gravity on the surface of the earth, multiplied by re, radius of the earth squared. So if we plug this in to our expression here, then we get g times me is replaced by g times re squared, and so we get little m times little g times re squared divided by re cubed. And then this re squared will cancel with the re cubed, so we will have mg over re. So another way of writing this force Fg as a function of r is equal to, we'll write it in two ways. The first way was negative g little m capital Me over re cubed multiplied by little r times little r hat. And then the other way of writing this is equal to negative mg over re times r times r. So the next step is to write the equation of motion for the ball or the object that we threw down the hole through the center of the earth. So in order to write the equation of motion, we essentially go to Newton's second law, which is F equals ma. And in this case, the force is the gravitational force equals mass times acceleration of the object. And if you think about it, the ball is moving in the radial direction for the Earth, so this acceleration is nothing but double time derivative of the radius. So it's m times d2r dt2, and that's along the radial direction. So now we can take this and put this together with our previous expression for the gravitational force, and then we get m d2r dt2, and I'm going to only write the scalar parts of this equation. So m d2r dt2 equals negative mg over re times r. All right, clearly the mass little m falls off from both sides of the equation, and we get d2r dt2 plus g over re times r is equal to 0. So this is again a second order differential equation. It just looks like exactly like our spring mass system differential equation, which was of the form d2x dt2 plus k over m x equals 0. So this k over m is the same as this g over re over here. Now if you also remember our simple harmonic motion for a pendulum, then in the case of the pendulum, the equation that we had looked like d2 theta dt2 plus g over L theta is equal to 0. And there g over L took the place of the k over m. And these are all the g over re, the k over m, and g over L. These are essentially the square of the angular frequency. So in this case, omega square is g over re. Okay, in the case of the pendulum, the omega square was g over L. And then for the spring plus mass system, the omega squared or angular frequency squared was k over m. Right, so essentially this is this problem where we threw a ball down a hole through the center of the earth is nothing but a simple harmonic motion. And look, it kind of resembles a pendulum where the radius of the pendulum is the radius of the earth. So as if we have a pendulum with the length of the string equal to the length of, yeah, equal to the radius of the earth.